Alrighty, welcome everyone to Data Engineer Camp's Demo Day. Over the last 16 weeks, the students have completed a intensive data engineering bootcamp, and I'm just going to walk us through a brief introduction to what the bootcamp is about, followed by the project presentations themselves, and finally a short networking. If we do have time for it, we'll do some of that as well towards the end. So a bit about the bootcamp. The current cohort consists of 23 students from all around the world. We have students residing in the US and Canada, Oceania, which consists of Australia and New Zealand, parts of Europe, Asia, Middle East, and South America. So quite a diverse background and from multiple different time zones as well that the students currently reside in. And here is a brief overview of what the students have covered over the last 16 weeks. The first 4 weeks was focusing on data engineering foundations, building ETL pipelines using low-level tooling like Python and SQL, as well as cloud technologies, Docker, Git, and so on. Then they covered off concepts around data integration using frameworks and tooling like Airbyte, big data processing with Snowflake and dbt, data modeling, and we touched on topics like dimensional modeling, and we applied it through technologies as well, like dbt and preset. Big data processing with Databricks and Spark, data orchestration with Dagster, streaming with Kafka and ClickHouse, and finally, we covered up the last topic of CI/CD with GitHub Actions and infrastructure as code using Terraform. Just a heads up, the next cohort is kicking off on Monday next week. So if you are interested, we have some seats still available if you want to sign up for that. All right, we're going to kick us off with a couple of presentations today. We have the Formula One ELT pipeline by Douglas. Don't see Gabrielle here yet, so we might skip over Gabrielle's presentation and jump into Madyar's presentation on heart rate stream after Douglas's. The presentations will run for about 10 to 15 minutes per person with 3 minutes of Q&A. If folks, if Kat, you have any questions, or Douglas, you have questions, or if I have any questions, we can ask that as well in the chat. All right, so without further ado, let us begin. We'll kick us off first with Douglas's presentation. Over to you, Douglas.
Sharing the screen. Okay, so my project is about Formula One. And for those who do not know, Formula One is the most prestigious motor racing competition in the world. And when we talk about Formula One, we actually talk about two different championships. We have the Drivers' Championship, and we also have Constructors' Championship. And so in this project, we aim to create an ELT pipeline that will help Formula One enthusiasts kind of like answer some of the questions like who was the champion driver and the champion constructor in each one of the years, starting from 1950 into 2023, or which countries had the most races, or what are the most dangerous circuits, and so on. So behind this ELT pipeline, this is this solution architecture that we have. So starting from the left, as a data source, we have a PostgreSQL database instance that is hosted in AWS RDS instance. Then we have Airbyte as our data integration tool. And in this case, it is hosted in Amazon EC2 instance. The data is stored in Databricks Lakehouse, which uses Data Lake as a storage layer. And it is transformed using Apache Spark, still inside Databricks environment. We serve the data using preset dashboards, and all of this is orchestrated using Dagster Cloud. So in the following slides, I will go into some of these steps in a more detailed manner. So the first one is ingestion. So as I mentioned, we pick Airbyte as a data integration tool. Again, it is hosted on Amazon EC2 instance. Airbyte is basically responsible for connecting to the PostgreSQL database, extracting data from it, and then loading into the Databricks Lakehouse. The way that it loads is to an incremental append sync mode. And in order for us to do that, Airbyte requires us to have kind of like a cursor field, which in this case is the updated at column that represents like the timestamp at which the records for a given table were last updated. Moving on to the next step, we have transformation. So Airbyte will load the data into what we call bronze layer. So basically the bronze layer includes everything, all the raw data from the PostgreSQL database. Once the bronze layer is created, then we want to create what we call silver layer. So the silver layer will basically read data from the bronze layer and then perform some basic transformations, like we'll flatten some JSON fields, we'll deduplicate records, like rename some fields and so on. And at this stage, we also create surrogate keys. One important thing to note is that we are also performing data quality checks with the data in transit from the bronze layer to the silver layer using great expectations. The way that we load and create tables in the silver layer is via an upsert operation. And finally, we have the gold layer. So basically, the gold layer will read from data from the silver layer and then perform some additional transformations like joins, like calculations, and so on. And then it is at this stage that we also create one big table, which is going to feed the preset dashboard at the end. So this is the ERD diagram that we have at the gold layer. Basically, we have 4 dimensional tables and 2 fact tables. We have 1 dimensional table regarding races, like what the name of the races, where they are located, like the country, latitude, longitude, and so on. We have a dimension table for drivers, like we have information such as the name of the driver, the country that the driver was born, and so on. Dimensional information about constructors, so information about the name of the team, the nationality of the team. And then we have a dimensional table for status. So what happens is that for at the end of a race, different drivers, they can basically, some of them will be able to complete the race, others won't. Some of them will get into an accident, maybe the car broke or something like that. So each one of this represents a different status and they are recorded in the dimensional status table. So finally, we have the 2 fact tables, one for race results, the other one for sprint results. Even though the fields are the same, they actually represent 2 different business events. Race are basically the longer version of a sprint race, or the opposite. Sprint, they are like a shorter version of race. They usually last 30 minutes. They don't have pit stops. So sprints, I think they were created back in 2021. And for race, we actually have data since 1950. So this is the reason why we have the 2 fact tables, separate tables, right? Separate entities. Moving on, we'll have orchestration. So all of the data transformation happening inside Databricks, and the relationship, like dependencies, dependence between like the bronze tables, silver tables, and gold tables, they are managed using Databricks workflow. But in order for us to kind of like connect Airbyte ingestion with Databricks transformations, we actually use Dagster Cloud. So in this case, we only want to trigger Databricks transformations if Airbyte successfully loaded the data into Databricks Lakehouse. So at this point, I'm actually going to stop sharing my screen and we can move on to some of the tools. 1 second. Yeah. So let's start with Dagster. Basically, there are 2 ways for us to orchestrate our pipeline. The first way is using what we call asset jobs, and the second way is using automaterialized policies. So asset jobs, I guess, is basically the traditional way that we orchestrate pipelines. We basically tell Dagster like how often we want the pipeline to run, in this case, every 5 minutes. Whereas automaterialized policies is basically a more, I guess, declarative approach, as you can see here, when we basically tell Dagster like when and how assets should be automatically materialized based on certain conditions. Like one specific condition can be, for example, changes in the upstream data, like freshness requirements, or even specific schedules, right? So those are the 2 ways that we can orchestrate a pipeline. One example that I wanted to show here is also, let me see here. Every run actually kind of like create logs, and those logs are sent to Slack, right? So these are the 2 examples of failing. When the pipeline failed, these are 2 examples when the runs actually completed successfully. One thing that is important to note is that you can see here you have schedule, which means that this here is a run that was triggered using job assets, while this one here doesn't. So it means it was triggered using automaterialized policies. I guess we can move on to the preset dashboard. So basically, the preset dashboard have 4 different tabs. The first one is an overview tab where I talk about like what's everything about Formula One, a brief explanation about the data set. And then we have 3 additional tabs, one for drivers, one for constructors, and one for circuits. I guess we can, I'm not going to spend a lot of time explaining each one of this, but maybe we can take a look at some of the charts in the circuit tab. So here is the circle location. Basically, the color grade represents the number of races that happen on that specific country. We can see that Italy is basically the country that had most of the races. And the little, I guess, little circle, red circle, represents the number of accidents that happen in that country, right? So at the bottom, we can actually see the number of accidents per circuit. So in this case, the most dangerous circuit is, for those who know Formula One, is Circuit de Monaco, followed by Spa-Francorchamps, which is located in Belgium. I guess finally, we can move to the GitHub repository. So here we can see, I guess, 3 CI/CD workflows. The first one is the linter, which is kind of like basically responsible for like flagging improperly formatted SQL and Python code. We then have the serverless branch and then the serverless prod deployment. So those two are basically workflows that are responsible for pushing the code to Dagster cloud, right? The serverless branch will kind of like create staging environments of the Dagster code. And it's going to happen every time you push code to a branch. While as the prod deployment is going to only trigger when you actually merge and push code to the main branch. Yeah, so everything that we talked about is documented in this repository. And at the end, there's some like security tips or notes on security rather, talking about like how you can whitelist some IPs to not kind of like make your EC2 instance publicly available. And the same thing for the RDS instance holding your PostgreSQL database. So yeah, that's my final project.
Oh, thanks, Douglas. We have about 5 minutes for questions now. If anybody wants to ask your questions, so drop your questions in the chat or feel free to unmute yourselves to ask Douglas anything that jumps to your mind. I can kick us off with just one question first. How is Dagster orchestrating the Databricks tasks? Is it creating some kind of representation of one like transformation, or like how is that happening? And you could like maybe show us in a diagram as well, like the asset graph of how it looks like.
Yep. So let me go to assets, global assets. So this is how Dagster see the Databricks workflow. It's one single asset. And basically the Databricks workflow is this one here. So this is where, I guess, let me do this. So again, this Databricks workflow is like responsible for mapping the dependencies between like bronze tables, silver tables, and gold tables. So Dagster is only like calling that specific workflow and triggering a job.
Ah, cool. Right. So Dagster calls a workflow, and then the workflow in Databricks defines the relationships or the DAG between the transformations tasks. Is it possible to actually create an asset representation in Dagster? So have it all in Dagster as opposed to the relationships inside of Databricks?
That's a good question. I haven't researched about this, but I believe it is probably possible.
Yep, cool. All right, thanks, Douglas. Anyone else have any questions? Feel free to unmute or drop your questions in the chat. Yeah, I guess I can ask one more whilst people are thinking, getting the thinking caps on. So I guess like there's kind of differences, like there's two competing products when it comes to data warehousing. I hear a lot about Databricks and which is what you use, and also technologies like Snowflake. What made you ended up deciding to use Databricks over something else like Snowflake or BigQuery, for example?
I guess the biggest one was for learning purposes. I guess Spark was something that I've only worked back in 2019, while as like, for example, BigQuery, Snowflake, more like BigQuery are things that I kind of like work on a daily basis, right? Snowflake was the data warehouse that I used in the past, while as BigQuery is the current data warehouse that I'm using in my day-to-day job. The second reason, I guess, I wanted to also, another reason is because I wanted to use a different tool other than dbt, which is something that I also use on my day-to-day work. And yeah, I guess in general would be learning purposes.
Cool, that makes sense. All right, I don't see any questions coming up. But yeah, if folks in the audience wants to ask anything along the way as well, feel free to just drop your questions as always. All right, thanks, Douglas. We're gonna jump on to our next presenter now. So our next presentation is on the heart rate stream data from Madyar. So over to you, Madyar.
Hey everyone, how are you? Okay, can you see my screen? That work?
Yeah, that's showing.
Great. So for this presentation, I decided to do a little bit of a combination between streaming data and storing the stream data into a data warehouse. So my project overview is, what I was thinking is, if let's say you're wearing an Apple Watch, it collects heart rate data over time for a certain user during a certain activity with a specific timestamp. And that data is obviously processed as stream data, but what if there are researchers, what if there are analysts that want to analyze the historical heart rate data over months and years on end, right? So for that, we would need to store it into a data warehouse. And this is the project architecture that I chose. So first we have a producer.py file here. It's simulating heart rate data. I'll show you like a JSON object that it's sending to a Kafka topic that is hosted inside of Confluent. And then using Confluent's sync connectors, we actually sync it into an S3 bucket where it's stored for persistent storage. Then we have our own OLTP data system, like a mock data system, where we have our users data and our activities data. So let's say, again, your Apple Watch, and you have a database with all your users, right? And then what we do is we take both those data records, right, from the OLTP system and the S3 bucket. Everybody takes them and then it puts it all into our data warehouse where we run dbt models, dbt transformations. And all of this is orchestrated by Daxtra Cloud. And then we can also connect Tableau in order to get a semantic layer and create some visualizations of our data. So the producer.py script looks similar to this. What we have is a user ID. We have a specific heart rate. We have a timestamp written in Unix time. And then we have a meta column with the activity ID, location, latitude, longitude, right? And this is all containerized and hosted in an ECS instance that is continuously running. So what I did was I had to set up the Kafka topic. Here, the Kafka topic is divided into 6 partitions with a 1-week retention time. Very simple. The 1-week retention time slightly bothered me actually in the end because of data processing. The way Kafka works apparently is that it does not do the emit final data processing until the retention time expires, and 1 week is just too long of a time. But yes, then I had to configure the S3 bucket connection here with an IAM role, and here it's connecting the sync, and here is how it looked when data was being registered into Kafka topic, right? And here we see some metrics, and this is data being written into the S3 bucket itself, right? Then when it comes to generating the mock OLTP database, what I did was I had the Python script create mock data, like mock CSV files, and then all I had to do is just load these mock CSV files into a Postgres database that is hosted on an RDS instance. And the data sort of looks like this. So there's activities data here. And as I mentioned before, there's also users data with a lot of columns, right? Then with the integration with Airbyte, what I did was I set up CDC for the Postgres database. And CDC allows us to also not just see the incremental updates, but to also see hard deletes in our system. And the way I really wanted to set this up for the data warehouse is I wanted to have all the historical records be persistent inside of the data warehouse for our researchers. So yes, then I have the S3 sync, and the S3 sync just takes all of the globs, as you can see, from the file system. Here, with the CDC sync, usually in the sync mode, you would have a default value of incremental append plus deduped. However, I didn't want to overwrite any of my data. I just wanted to append the data. And what I really wanted to do was I wanted to take certain activities, certain users, update them, and also create type 2 slowly changing dimension with them. So let's say a user has changed their address. Now we have a new user record generated from that with the valid address, and also like a previous user record as well. So for historical analysis. The S3 Snowflake connection was also done with an incremental append. So as you can see, I am never trying to overwrite the data. All of the updates to the data have to be monitored by the warehouse itself. And then when it comes to the transformations with dbt, so this is how the raw data looks like, actually. Here, as you can see, we have the activities table, heart rate stream table, users table. We also have a country codes table. This is a seed file that dbt generates. I stored it here for now, and the seed file is just used for testing. And then this is an example of how the users table looks like. For example, we have a user, certain airbyte columns, right? Sex, race, height, weight, address, etc., etc. The lineage graph created by dbt looks similar to this in terms of our models. So what I did was I created dim dates and dim times models. Dim dates is actually taken from an external package by Catalogica, and dim times was just manual SQL code. And both those dimensional tables are meant to help the researchers aggregate the data for certain hours of the day, for certain dates, specific dates, like weekends and everything like that. Then here it's quite simple. Just like in Doug's project, staging tables just do a little bit of JSON flattening, renaming. Unlike in Doug's project, my surrogate keys are generated inside of the dim activities and dim users. And the reason why fact heart rates actually needs to load after dim activities and dim users is because it does a join. Because if I can go far enough, as you can see, I here have the user ID, right? But I don't have the user key. And in order for it to join with the correct user key, what I do is, let's say there are different versions of the user ID. So there's the same user ID, but there's one that was the previous version, and there's one that is the active version. What I do is I check the timestamp, and I check if the timestamp fits into between the start date and the end date of that specific user ID. And I can show you the dbt code for that, the ginger code for that. And this is more of a complex lineage graph that dbt docs generates for me. So these are just some test files as well that I have. And this is how the warehouse looks. So as I said, we don't really want to have the user ID in our fact table or the activity ID. We want to have a specific user key that this ID applies to, and the activity key. We also have a date column that has a direct link to date day, and at the time that has a specific time period. So written in seconds, right? We do a bunch of window calculations, and this is how our warehouse looks. And as you can see, for the dim users and dim activities, we have a start date and end date columns that allow them to be type 2 slowly changing dimensions. And active versions have an end date of null. So here's, for example, I did a few updates on my Postgres database on my OLTP system, and on this specific user ID, and this is how it would automatically be processed in my warehouse. So there's a start date, and then there's the end date. So we see here, this specific version lasted for 20 minutes, this one lasted for an hour, and this one lasted for 1 more week. And then this is the current active version of that specific user record. I did it with some other user records here as well. So as you can see, start date and end date, and you can also see that the end date is the same as the start date of the newer version of the later version. Here's another one. And this is how the fact table looks like at the end. So we have a user key, activity key, event date, event time, a date time, event date time column as well. Then this is all orchestrated by Daxter. So for Daxter, we have to, for Daxter Cloud Serverless, we have to run all these GitHub workflows. However, there's a little bit of a problem with Daxter Cloud Serverless and dbt deps, running dbt deps on Daxter Cloud Serverless. But there is a get around. There is a certain file you have to add. I can mention it. Yeah, let's mention it now, actually. It's inside, it's called Daxter Cloud post install.sh. And it's just a dbt deps command, right? But it has to be called like this. And then there are certain configurations you have to put into the GitHub workflows files. But it allows Daxter Cloud to properly run dbt deps when loading your project. And this is how the Daxter assets look like, actually. And why was Daxter chosen is that it has seamless integration with dbt, great integration with Airbyte. We can have a great outlook of our models here. And then dim dates and dim times, as I said, I want to have them persisted in the warehouse. They do not need to be refreshed every day or every month, right? Same thing goes to country codes, for example. They do not change. They very rarely change. However, all of the upstream data sources connected to fact heart rates, and fact heart rates is something that we want to be refreshed. And Daxter allows us to put a declarative asset materialization policy on a certain model, and then put an asset materialization of eager into the upstream models as well. And through that, we can also see how this works. So this is all running by the auto materialization policy. And as you can see, it's selecting 9 assets. So the 9 assets are the fact table and all of the assets upstream of the fact table. Yeah. So here it's generating the run. This is how it looks like. The run takes around 40 seconds, and then, yeah, 1 minute 30 seconds actually. And then for the visualization with Tableau, there were certain metrics created, right, for different user demographics. And here I tried to create a dashboard for the average heart rate during exercise for our European users. So maybe somebody wants to just see the users that are based in Europe and their heart rates, and they can have a pretty nice looking dashboard as well with certain metrics like how many heart rate measurements are there in aggregate, how many users are there in aggregate in Europe, how many countries are we representing, what's the average, etc., etc. So you can play around with it. Since this is a simulated stream, it's not the visualization layer is not more in any ways indicative or in any ways interesting, but still it's interesting to see that there are some differences here. For example, 140 and 128, right? A little bit of a heart rate difference. Yeah, I think that covers it. And if there are any questions, I would love to hear them.
Awesome. Thanks, Madyar. Good job. We do have a question in the chat from Yash. Yash is asking, in order to enable privacy for user data, is there some of the techniques that we need to think about when building ETL pipelines?
Yes, there are techniques. I think there's like column level security, so data masking as well, for specific columns. Here, this is more of a simulated user's data. So the script to create the user's data is a Python script, and it uses the Faker library and also the random library to create 10,000 user records. But in a real setting, of course, these would be #1 priorities, right? And this would be something that I would look into as well. I hope that answers the question.
Yes, thanks. Very nice. Okay, if anyone else has questions, just drop it in the chat or feel free to unmute yourself and ask your questions. In the meantime, I do have a question for you as well, Madyar. How does Airbyte know not to ingest the same files that it has already ingested before from the S3 bucket?
That I do not know. That I think is Airbyte by itself. Somehow it does know because it doesn't. I did check this on the S3 bucket, but my understanding is that it keeps a log of every file that it looked at, and it has like there's a column called Airbyte file last modified. So it looks at if the file last modified is before or after the last log, essentially, right? So if a file was modified, let's say it's the same file that it already ingested, but it has new records in, I think it would show up in the logs as well.
Ah, okay, cool. That makes sense. So Airbyte's keeping track of the S3 metadata and then looking out for files that are newer or modified.
Right.
Cool. And then why I saw that you have Kafka and then you have a step to take data from Kafka into your S3 bucket. I guess the question is why not take the data from Kafka and land it directly into Snowflake? Why do you have that intermediate step of having an S3 bucket between Kafka and Snowflake?
I think Kafka is meant more for right, it's meant for microservices and also for streaming data. And I do not know how well it is when it comes to like data integration, just ensuring that it's only ingested once and only once, right? Whereas I think with something like Airbyte and a batch processing, it would be much more easier to handle. Also, on an SD bucket, I think if the data is persistent, we can reuse it as well. And I used to work with machine learning engineers who prefer to work with files inside of a data lake. So I think this is why I chose this implementation for the project.
Yeah, cool. That does make sense. Yeah, and I think Kafka has like retention policies. I think yours is set to 1 week from your demo. I think the
Right.
screenshots you showed was like 1 week. So if like, I'm guessing if the sync for Airbyte only happens like once a month or something like very irregularly, then, there might be data that's not stored anywhere else. Like we lost the data. Whereas if we can persist it into S3, like what you're doing here, that's good for historical purposes or longer, like lower frequency refreshes.
Exactly.
Very nice. All right, I'll pause here. Does anyone have any questions you want to ask Madyar? Aniket is asking in the chat, how is the current or latest version of the user being identified in the data warehouse? I think this is more relating to the slowly changing dimensions. How's that? Yeah, how do you
Right.
know the latest user?
So, well, with the Airbyte CDC, we have the Airbyte CDC last modified column and Airbyte CDC deleted add column, right? If let's say a row was deleted add. As I said, we do incremental append. So what it just does is it appends in your row. It doesn't overwrite the previous row. It appends in your row. And I just look at the timestamp. I look at the maximum timestamp, and there is a lead function in Snowflake that I can use to sort and then put in the correct start dates and end dates for the users. So there's a little bit of a playing around. You can find it in my project's GitHub repository inside transform, inside like dim users and dim activities, models. Maybe I can show you right now, actually.
Yeah,
That's okay.
that would be good.
Right. So this is my GitHub repository. So transform models, and then I go serving, and then inside dim users. Okay. So I have different CTE statements here, but what it essentially does is I just take well, I look at if the row is deleted, then it is deleted. Else I take the updated. I wonder where okay, here. And it is called the lead last update over partition by. So I don't even use the Airbyte's last update column. I use the last update column from our transactional system, which I think is even better for this case scenario. So yes, this window function lead allows us to take in the previous last update version for this specific user ID, and it will be null if there is no previous last update version as well. So this is how it works. Yeah. Does that answer your question?
Yeah, looks like Aniket's happy with that response. All right, any other last questions for Madyar before we hand it to the next presenter? Oh, all right. Up next, we have actually Gabrielle. Gabrielle, I can see you just you joined the call not too long ago. Are you ready to present?
Yeah, all good. Sorry, being a bit late.
No worries. Yeah. So Gabrielle is going to be talking to us about Strava and how she built a data pipeline with Strava data. So I'll hand it over to you now, Gabrielle.
Yeah, sure. I'll share my screen real quick. Yeah. Can you see the slides?
Yep.
Yeah. Hi everyone, I'm Gabrielle. I work as a data analyst at MSKI. It's based in London, and it's a health tech company dedicated to improving patient outcomes by automating administrative processes and assisting surgeons in tracking and supporting patient recovery. And I'm currently in the process of transitioning to a data engineer role. So personally, I'm quite passionate about fitness, although ironically not running. But this project was kind of an opportunity for me to merge my professional interests and my passion for fitness. So kind of led me to develop this project, which leverages data from Strava into the data pipeline. So what is Strava? It's essentially one of the leading fitness apps that connects millions of athletes around the world. It not only tracks their athletic activities, but also fosters a community where users share, compare, and compete with each other's performances. So the project aimed to develop an advanced data pipeline to provide in-depth analysis of the athlete's performance from Strava, and we may the scope was basically using the data from two users, myself and one of my friends, and so the system essentially helps to monitor fitness progress, comparing historical performance and planning maybe training sessions more effectively in the future. And by doing so, potentially athletes and coaches can identify strength to build, better training plans, and making this tool quite valuable for optimizing training, essentially. So the solution architecture was extracting data from Strava API. And once the data was pulled, it was staged in PostgreSQL hosted on AWS RDS. And then Airbyte steps in and with CDC to ensure real-time updates and that everything is managed efficiently, keeping the data synchronized without overloading the source. So then the data moves to Snowflake, where dbt performs transformations, turning raw data into a more refined format, ready for in-depth analysis. And then it not only maintains kind of the data integrity, but ensures that it's precise and actionable, so that we have kind of more refined data in the end. And everything was orchestrated with Dagster, Dagster Cloud specifically, and which coordinates the various stages from extraction to transformations, and everything, ensuring like everything is on schedule and running without any issues. Then lastly, I used preset to visualize the data and presenting it through an interactive dashboard that allows users to kind of explore and drive some insights. So the key considerations in designing the architecture were efficiency, scalability, and accuracy. So I've structured the pipeline to minimize the load and source system using the Airbyte and everything, and then to handle increasing volumes. Accounted for the fact that it might potentially expand to more users, the complexity of data, and so quality controls like tests. So the warehouse here utilized a kind of star schema for efficient data transformations and usage. So it features dimensions like date, activity, location, and athlete. Then I've created a dim athlete as slowly changing dimensions to track historical changes in the athlete's profile. Essentially, if I were to move countries, it will be depicted or something, and in the user profile. So it would allow essentially to track things over time. As I mentioned earlier, the entire data pipeline was orchestrated in Dagster Cloud. So it handles dependencies and jobs scheduling. So then dbt is also managed by Dagster Cloud, and all the data transformations with dbt essentially. Also, CI/CD is automatically employed with Dagster Cloud, and we can also add some extra tests, which again would be hosted with GitHub Actions to maintain the high standard of code quality, and to automate the deployment process. So to ensure that everything is robust and scalable. So for data visualization is powered by preset. So it converts complex data sets like this one into quite nice interactive dashboards. And the tool allows users to drill down some specific data sets, provide customized insights like these. For example, we have activity frequency by time of the day, and essentially it helps to identify peak hours maybe of athlete activity, so which can be valuable for planning training sessions, understanding personal performance patterns, and basically optimizing schedules for workouts. Then we have obviously breakdown by activity types, and this maybe to get a quick overview of training patterns regime, and to find some sort of balance and workouts. Then we can see as well the location analysis, to see maybe, it'd be useful to know where athletes train most. So maybe potentially scheduling some sort of organizing events and promotions. Then performance tracking to monitor progress in real time. Then stuff like kudos per activity, which is this kind of a social metric, so it can be an indicator of engagement and motivation from your peers. So maybe activities with more kudos would kind of have positive correlations with performance. To essentially the setup and deployment to get everything up and running, when I configured access tokens for Strava API, set up Airbyte on AWS EC2 instance for data transfer, prepare dbt models and to transform into Snowflake. And the deployment strategy was to facilitate a smooth setup process, ensuring consistent, reliable data flow from development to production. It was used security groups and AWS Secrets Manager to kind of limit the IP addresses that to have our data secured, and yeah, so to manage access. So for the future, I guess the plan would be to expand analysis to include more athletes, more users, to kind of have more data to play around with, maybe to have more sophisticated visualizations, maybe some machine learning models to apply to the data as well. Regarding the pipeline itself, I guess stricter security measures to kind of have to better safeguard the data in the system, and essentially, yeah, just improving the functionality and reliability of the pipeline. Yeah, so thank you very much. And yeah, any questions? We'll be happy to answer.
Awesome, great presentation, Gabrielle. I'll kick us off with a question, and then if anyone else have a question, feel free to drop it in the chat or unmute yourselves and ask away. The question I had was around, you mentioned around scale, like eventually you want to scale out and have many more users jump onto the platform and upload their data to Strava, and then you can analyze it. I guess like how does your current data modeling handle scale? Like if you have lots and lots of users with lots of events, is your pipeline designed in a way that's going to run efficiently? And yeah, what sort of considerations have been thought out?
Well, essentially with AWS, once you have more data, more users, it's gonna scale up on its own. So it's kind of taken care of. The storage, as I understand. So whenever, I don't know, like tomorrow we have like, I don't know, another 1,000 or whatever, like 100,000 users I think it will automatically scale up to the number that we're going to be facing. But also for the analytics hard side of it, it's, well, Snowflake is a columnar engine, so it's quite robust at summarizing large data sets when we just want to have some sort of filter on something specific, and it's much faster than, let's say, if we're dealing with just Postgres, for instance. Well, at our work, we're still using Postgres, and I can tell you that it's a lot worse in that kind of world. But yeah, and also the scheduling would allow for kind of relatively frequent updates of the data. Maybe right now it's daily, but if there will be any kind of requirements from, I don't know, customer success team in the future or something, that we need more kind of frequent updates to know exactly, like on an hourly basis or something, how many users we have and stuff like that, it's also possible.
Yeah, cool. And did you look into any kind of like incremental way of processing data in your data models, and also like with the data ingestion side of things?
Oh yeah. So I used Airbyte increment, append, and deduped method for data ingestion. So whenever something gets updated, it will trigger Airbyte to kind of refresh, kind of to ingest the data and see what are the differences are, and kind of update the records or delete or insert new data, or just update existing rows.
Cool, very nice, Gabriel. Okay, I'll pause here to see if anyone else have any other questions. Okay, just one final one from me, because you mentioned data quality, I think, as well. So did you implement, or how did you make sure that the data results are kind of what you expect, or within the range of what you kind of expect?
Yeah, so I've looked at the raw data. I kind of had running a few tests to check, let's say, just like simple, as simple as like whether the number of records at the kind of final stage of my data transforms are the same as the kind of raw data. And there were also a few DBD tests as well that just like assure that the data makes sense. Yeah, so as I said, another kind of improvement would be to have a more robust testing. So the tests that I've implemented were kind of at the not at the stage that they should be. So it's like if we're talking about production, but they're just like a small things to just catch some issues here and then, but nothing to kind of like, yeah, if that makes sense.
Okay, yeah, that makes sense. Yeah,
Yeah,
I
yeah.
think you're probably using.
And maybe
Go ahead.
another thing would be to kind of also de-identify the data for the kind of analytics side. So because I don't think they would need to know who exactly was running this distance or anything, but to make sure that kind of data is not visible to everyone as well, maybe.
Yeah. That goes back to, I guess, Yash's question from that was addressed to Madyar. Yeah, around data privacy. So like, yeah, how do you make sure sensitive data isn't presented to people just reading a dashboard? Yeah, like names, date of birth, things like that. Cool. All right. I don't see any other questions in the chat. So, all right, I'll present my screen now. And thanks, Gabriel. Well, thanks to all three presenters. Thank you, Gabriel, Madyar, and Douglas, for your presentation. Good job. So if you'd like to give a round of applause, now is the time. Awesome. Alrighty. So we're gonna spend the last 15 minutes on networking now, just to kind of mingle around, have a bit of a discussion around like some topics around data engineering, so that we can all learn from one another. We have some really interesting guests here in the audience today. So yeah, we would really like to learn from you as well, and hear from your experiences, and for us to also share, for the students themselves to also share their experiences with you. So we're gonna just hop into 15 minutes of networking now. I have 2 questions to ask, but for the interest of the people on the recording, I might just stop the recording and we can just have a chat. So stop the recording.